Hi everyone. This is the second concept that you have to master in the stoichiometry chapter. And I'll start with this video, which will discuss a series of concepts, starting with the mole concept and concept of molar mass, as well as Avogadros number. So the first thing to start with is just what is called a mole in chemistry. The way you should think about it is as in everyday application, when we work with a large number of quantities, in this case atoms, the unit that we use to count each atom is really not convenient to use. So in this case, to use the AMU unit or the atomic mass unit is not convenient. This is analogous to when you're buying bread, for example. If you want to count each of the bread, usually the bakers don't really like for you to buy just one or two bread, but they prefer to count in terms of dozen, which is of course equivalent to 12 pieces of bread. Or sheets of paper. That's another analogous situation. You don't really go out and purchase one or two sheets of paper. You usually purchase them in the form of a ream, which is really a unit that denotes 500 sheets of paper. So we have a similar situation with atoms because it's really impractical to talk about counting one or two atoms. The type of number of atoms that we work with when we work with grams of material is really a huge number of atoms. So we need to have a quantity that denotes a certain number of atoms, and that quantity is what we refer to as a mole. Okay? So that quantity, a mole, is equivalent to a given number of atoms. So then the question is, how many atoms are in a mole, okay, or particles? So the actual definition, the formal definition, which is of course the SI definition, the Système International definition of a mole, is that it is the amount of a substance that contains as many elementary entities, and really that's just a fancy word of saying as many atoms or as many ions, if we're dealing with ions, as many molecules or as many electrons, if we're talking about electrons or other types of entities, as many entities as you can find in 12 grams of a pure carbon-12 isotope. Now you should remember that when we talk about atomic mass in the previous concept, right, we also use the carbon-12 isotope as a standard. So in this case, we are using the same standard, which is the carbon-12 isotope, to define a mole. So we're saying that a mole is basically a number of, the same number that would be the number of atoms that you can find in 12 grams of a carbon-12 isotope. So then the question is, well, how many atoms is that, right? What is that number? Well, we can calculate this, okay? Because we know that first off, we have 12 grams of the material, which is carbon-12 isotope. We also know that in a carbon-12 isotope, the mass of a carbon-12 isotope is 12 AMU. Now what we have to do is just relate 12 grams to 12 AMU. Now we know that 12 AMU means 12 times the mass of a proton, right? Because 1 AMU is equal to the mass of a proton, okay? So you can do this calculation, which I'll do in the next slide. Okay, so then going back to our question, we're asking how many carbon atoms are there in 12 grams of a pure carbon-12 isotope. Okay, so as you remember, each carbon-12 isotope has a mass of 12 AMU. And 12 AMU is really, remember that each AMU is equal to the mass of a proton, and the mass of a proton is 1.67 times 10 to the minus 27 kilogram. Or you can also convert this to gram, but right now we'll just do it in kilograms. So then the answer we get here in terms of kilogram is 2 times 10 to the minus 26 kilogram. Or if you convert this to gram, you just use the appropriate conversion factor, you should get 10 to the minus 23 grams, okay? The reason I want to convert it to grams is because I was given 12 grams of the material, so I wanted to have the same units. So then to get the number of carbon atoms, I just need to divide the total mass, which is 12 grams, divided by the mass of each atom. You remember that this is actually the same exact operation we talked about in the atomic mass chapter per atom. And that should give us the number of atoms that we have in a carbon atom. And if you do this in the 12 grams carbon atom, if you do this, you get this number here. 6.02 times 10 to the 23rd atoms. Okay? Okay, so that number that we just calculated, 6.022 times 10 to the 23rd, is what we refer to as an Avogadro's number. So this is defined as a mole. Okay, so anything that has this many counts of particles or substances or objects is referred to as a mole. Okay, so if you have a mole of oranges, for example, that would mean that you have this many oranges in that particular collection of oranges. And as it turns out, that if you have that many oranges, it'd be equal to about the size of the Earth. Okay, so it's a really big number, and that's what you have to appreciate in terms of the size of this number. Okay, now that we have this convenient definition of a mole being equal to 6.02 times 10 to the 23rd of particles, we can use this Avogadro's number to calculate the mass of a mole of any substance. For example, here I'm just showing you in terms of oxygen atoms. If you have 1 mole of oxygen atoms, the question is, what is the mass of that oxygen atoms would be? Well, we know that 1 mole of anything is 6.02 times 10 to the 23rd. So if it's oxygen, it will just be 6.02 times 10 to the 23rd oxygen atoms. We know that each oxygen atom weighs 16 AMU, right? You can find this out from the periodic table. And 16 AMU means it's 16 times the mass of a proton, which is this number. So then if I want to figure out, so then the mass of a oxygen atom is just 16 times this number, which is a given number. Okay, I'm not going to calculate that because I'm going to write it out in a longer form at the bottom, the next line. The mass of 1 mole of oxygen is therefore the mass of 1 oxygen, which is 16 per atom. Multiply that by the kilogram to AMU conversion, okay, which is the mass of a proton, right? And then we know that that's 1 oxygen atom. If we want a mole of oxygen, it will be 6.02 times 10 to the 23rd atoms total. If you work this out on a piece of paper, you notice that all the units will cancel out. And what you get in the end is 0.016 kilogram, which is of course equals to 16 grams. So in other words, 1 mole of oxygen atoms will weigh 16 grams. Okay? Now, one thing I want you to notice at this point is you notice that the number, the value of the mass, whether it's 1 oxygen atom or 1 mole of oxygen atom, it's the same value, is 16. But the units are different, right? In this case, you have the AMU unit, which of course means it's a very small mass, right? It's 16 times this number, which is a very small number. If you have a 1 mole of material, you have 16 grams, which is a much bigger number in comparison to the 16 AMU, okay? But you have to notice that it's the same value, okay? So whether you're talking about 1 atom or 1 mole of atom, you get the same value, except that the units are different, okay? Now, if you have compounds, you basically do the same calculation like what you did before with molecular mass, except that now you're going to just add all the molecular masses together. You know, you get the molecular mass and then you convert it to the actual mass by using Avogadro's number. So in this case, let's say we're talking about CH4. Remember, this is our methane molecule. The molecular mass we calculated in the previous video to be 16 AMU. So that means that if we have CH4, each CH4 molecule has a mass of 16 AMU. 1 mole of CH4 means that there are 6.02 times 10 to the 23rd, in this case, molecules, not atoms, okay? So then the mass of 1 mole of methane would just be equal to 16 AMU per molecule, right? And then each AMU is equal to this much mass, 1.67 times 10 to the minus 27 kilogram. And then in 1 mole, there are this many molecules. So if you multiply everything together, you should get this number, 0.016 kilograms or 16 grams. Okay, so the mass of 1 mole of methane is the same as the mass of 1 mole of oxygen, even though they're two different substances, just as it happens because the atoms that make up those, the molecule and the atom of oxygen have the same mass, okay? So in the next video, I will talk about this concept of molar mass and then how to use both Avogadro's number and molar mass to allow you to make conversion between microscopic quantities like the AMU to macroscopic quantities like the grams and later on liters and so on.